Yeah, so of course robots would be nice to have, and I would love to show off our robotic fabrication process, but that's not possible here. But at the end of the talk I have a video for you. So I'm going to present our work on a flexible mold that can be used to produce customized, for example, facade panels, and of course it can be combined with 3D printing. This is a joint work with my co-authors, and most importantly Zheng Wang from University of Toronto. He did a lot of the computational work for the project. Now, you know freeform facades, you know this problem of how to produce these kind of freeform panels, and I'm now talking about facade panels all the time, even though this whole idea and the technology could be used to produce maybe even much more useful things. For example, you could use it to make a more efficient ceiling slabs or these kind of things, but for simplicity, let's call it facade panels for now. Now, since we are here, additive manufacturing, well, the naive approach would be, we can 3D print anything, so let's 3D print these panels. But that's not always a good idea. For thin structures, this can be difficult, and you always end up with this very distinctive surface texture, which you may like or may not like. For many applications, they are not desired. So, well, the next simple approach would be this kind of a brute force approach. This is what you all know. Yeah, we take a block of styrofoam and we CNC machine a mold. Then the surface has to be manually finished and sanded and coated, and then you can produce your perfectly smooth facade panels. But of course, that's hugely expensive and a waste of money, time, materials, and so on. And here you see the problem with this method. So the next idea that people usually have is this, like, yeah, there's an engineering solution to this. Let's just take thousands of computer-controlled pistons, and we can create our adaptable mold, and now we can make all of our freeform facade panels. This works. But I think it's not a very clever solution, because it's a hugely complex machine with many, many degrees of freedom to produce this slightly curved, smooth panel. That seems like over-engineered approach to this whole thing. So the other field, of course, where a lot of my previous work comes from and my expertise is in architectural geometry. And yeah, what if we look at geometric approaches to this problem? And one obvious solution would be, yeah, maybe we can build this from developable surfaces, for example. That would be great, because then we only have to take some thin sheet metal, we bend it in one direction, and we can very easily approximate our freeform shapes. But unfortunately, you end up with this very distinctive strip pattern or patch pattern, and you get these perfectly straight silhouettes. Maybe not a good solution either. You can do a little bit better by allow some bending, not only bending, but also to allow some stretching and compressing of your structure. This even works with glass. This is from one of my previous projects on cold bending of glass. You can get quite nice smooth surfaces, but only with slightly curved regions, of course. Now you can do even better if you allow your initial panel or shape to be already curved, and start with something that is already curved and then deform it a little bit more. This is great because, for example, in this project we showed that this allows you to reduce the number of different molds that you need by about a factor of n squared. Right? So if you usually would need 1,000 panels, now you need only square root of 1,000 panels. Different molds. That's great, but you still have to CNC machine these blocks. So still not the best solution. But this project played a very important role for what I'm going to show you now, because there we introduced Weingarten surfaces into a computational design process, and these Weingarten surfaces will be important later on. And I just would like to mention one property of Weingarten surfaces. They have a functional relationship between the two principal curvatures. And this is what this figure illustrates. You can see on the left-hand side what looks like visually the same surface, but then you have this illustration on the right-hand side. These plots the principal curvature direction 1 to versus the principal curvature curvature 2. And in one case, you see that this spreads out to some surface area, but in the other case, you can see that there's this functional one-to-one relation between the two principal curvatures. And this is the important property that allows you to reduce the number of different shapes that you need to produce your freeform facade, and it is also the key ingredients for the success of the project that I'm going to show you now. Now, the idea for our flexible mold is this. We take a really stretchable, thin, flexible membrane, we inflate it or deflate it, and this allows us to create all kinds of shapes. And the idea was really born from playing with these kind of things and noticing that you have quite a lot of control over the kind of shapes that can be generated just by imposing some boundary conditions. And this is what we then investigated. And of course, from this balloon setup, this needs a more engineered solution. It needs a machine frame. You need to properly support the silicon membrane. It has to have some details worked out, and it needs a control system that can digitize this shape or at least measure the deformation. But in principle, this is the same idea. You have this closed box sealed up with this silicon membrane. We can increase or decrease the air pressure inside the box, and this rectangular frame in the middle of this box, this imposes certain boundary condition on this membrane. And the design problem now is to find these boundary conditions. So for a given panel shape that we want to produce, we have to find these curves here labeled gamma that then stretch the membrane in such a way that somewhere inside, a bit away from these curves, we get the perfect shape for our panel. And you can imagine that this is a difficult inverse design problem because there's a very indirect relation between these curves and the shape that is produced inside this membrane. And yeah, if you start thinking about this problem as a computational design problem, optimization problem, it seems like a very nasty problem. And if you talk to computer scientists about it, they will wave you off and say, "Nah, this is too complicated. We don't want to do this." And this happened to me for a few years until I finally was able to assemble the team of people who actually were brave enough to tackle the problem. And it turns out, if you investigate this a bit further, it's actually not so bad. Because, for example, you have this large deformation of an elastic material. This is difficult to simulate, but in our case, we can actually stay in the linear regime of the material. And so you can find quite a bit of simplifications that allow you to tackle this problem. But in the end, it leads to this optimization problem that we have to find this set of support curves that shape this membrane here, omega, into the desired shape that we need to produce our panel. Now, this optimization problem, of course, needs an objective function, and I'm not going to bore you much with it, but of course, the distance between this membrane and our target shape, this is the objective that we have to minimize. As soon as this distance is very small, then our target panel fits onto this membrane, and we can produce the desired shape. And here is where these Weingarten surfaces come in, because this optimization problem is non-linear and non-convex and a bit difficult to solve. And what allows us to solve it is it needs a good initialization. We need a good initial guess for these curves. This is the key to the whole project. And this initial guess comes from Weingarten surfaces, because it turns out that Weingarten surfaces, more specifically quadratic Weingarten surfaces, closely resemble the shape of these membrane surfaces. And so what we do is we first take our panel shape, we approximate it with one of these Weingarten surfaces, and you can see the process here illustrated. The blue part would be our initial panel that we get from the designer. Then we find a panel very close to it, which is Weingarten. This is then illustrated by this magenta curvature relation. And from this, we get our initial guess. These here red curves that describe our initial guess for these boundary conditions. And from there, we start running our optimization. And this initial guess is very good. You can see this here, for example. Here we compare actual simulated membrane surface as an input, and we compare it to two approximations using Weingarten surfaces, and our Weingarten surface approximation on the right fits very well to this actually physical simulation result of a membrane surface. Here's another comparison with two different initialization methods, because instead of taking our Weingarten surface, another idea you might have is you just take the panel, make it bigger. Since it's a NURBS patch, you can just evaluate it outside its initial boundary, and you also get some curves. These would be the red curves here, and you can clearly see that this would be a very bad idea because it gives you some initial guess for these curves, which is quite far away from a good initialization. And then once you have this initialization, of course, there are a lot of optimization details to be solved, how to make this efficient, and you can read the details in our paper. And of course, it builds up on a lot of existing work from our group, but also from other groups. But once we have this all in place, we finally have like our pipeline ready. We take the panel from some panelization of the design, and we can approximate it using the Weingarten surface. We find this initial guess. We optimize these curves so that we have this perfect set of curves. Then we can fabricate this boundary or this box that imposes the boundary conditions, and then we can fabricate the panel. And this is how this looks like in practice. So instead of machining a complete block of material, we only do this like 1D cuts from MDF or plywood, which is very fast and cheap. And I mean, it's not zero waste yet, but the waste reduction is significant, of course. And then this frame that imposes these boundary conditions is placed inside the machine, and we close this cover. You've also seen that there was this laser sensor positioned. This is used to measure the deformation or the deflation process. So we then deflate it until a certain height is reached, basically. And we get this height, of course, from the CAD model. And now this inner part, some part inside of this box, this has now the correct shape for our panel. And on this mold surface, we can now produce the panel, for example, by 3D printing, but other fabrication methods, of course, would also be possible, or a combination of different methods. For example, we also try to 3D print a boundary, but then use a manual casting process inside to speed up this process. And here you can see the final result. And the nice thing is now, if all 3D printing parameters are set properly, you end up with one perfectly smooth surface. And you still have the flexibility of an additive manufacturing process, because we could add features to mount this panel on some substructure and these kind of things. Now, it's interesting to take a look at what kind of panels we can produce. And it turns out that we can produce all relevant types of panels. Here you can see a selection of a panel in the front, which is slightly positively curved. Then there's one with a large positive Gauss curvature. The next one has a negative Gauss curvature. We have these saddle shapes. And the last panel, it's not that clear in this picture, but we can even make panels where the Gauss curvature in some region of the panel is positive, but in some other region of the same panel is negative. So we can build these transition panels between different regions of a larger facade structure, for example. This is our final demonstrator, let's say, that we built a scale model about 1 to 10 of a freeform facade that was not specifically designed for this fabrication process, but we just took it and used it. You can see that these panels, they are made of gypsum. So we deliberately chose a material which is hard and brittle, which cannot bend in shape, because this is the important thing here, that the shape comes from this molding surface, and you can see that they fit together very well. Here's another close-up that shows you how these individually fabricated panels, fabricated using different of these frame structures to impose certain boundary conditions, fit together really well. Thank you very much.
So, any questions from the audience? Oh, there's one. I thought you presented too well.
Thank you for the presentation. I just have a small question for the geometries that you can explore. Does it have to be always a concave geometry, or judging by the system, does it always have to be?
Yes. So in this machine that you have seen, we can pull down the membrane by decreasing the air pressure, but we can also inflate it. Now, as long as we pull down and we have this box that creates these curves and the boundary conditions inside the machine, we can only create, let's say, these concave panels, or we have this concave shape and we pour something into it or we print into it. But this is not a real limitation of the process, because with a little bit of engineering you can design something that pushes down a similar frame structure from the top and inflate the membrane. And then you have the other side. But this is indeed important because you would, in reality, you want to be able to do both, because otherwise you might end up that some of your panels basically show the outside on the rough side of your 3D print, right? But yeah, in reality, it's not a big problem, because you just have to design this machine slightly different. To keep things simple for now, we haven't done this, but this is an easy to solve engineering problem.
Okay, just another quick question. With the printing process that you used, judging by the material, was there issues with the deformation of the material after printing?
No, but of course this is something that one has to consider. If your whatever casting or printing process leads to deformation during the curing process, then this is a problem, because then you will not get the panel shape that you want. So the panels, the printed panels, as well as these ones, they're all made from gypsum, not from concrete, because we didn't want the hassle of having to clean our printhead from concrete. It's a bit easier if it's just gypsum, and for the sake of this demonstration, it serves the purpose. But yeah, this is important, that whatever is cast or printed does not deform during curing.
Thank you.
I think here the colleague asked half of the question. How do you solve cracks or any failure rates? What's the failure rate of those panels?
Well, for these ones that we produced, it's 0, and there's no problem in, like, I don't know, because the size is so small, right? You don't have this problem that you would face on a large-scale concrete structure, that you always will end up with some cracks. At that scale, that we did this physical validation, this is no problem, because the panels are like 20 centimeters by 20 centimeters. In reality, of course, this might be an issue, but again, in a way, it's not, how to say, it's not our problem in a way, because we provide this surface, right? And then what you do on this surface, this has to be some already established casting, printing process using established materials. And if it works for CNC machined molds, it works on this mold.
Right, thank you.
Thank you. Okay, you mind to pass through the microphone? Yep.
Thank you for this very interesting talk. Florian, what is the largest scale you could imagine or estimate to produce?
That's a good question. So I think you have seen the size of the machine. This fits on a tabletop at the moment. The current machine is about 1 meter by 70 centimeters large. The panels that we make about 20 by 20, maybe 30 by 30 centimeters. So the next step now of this project is scaling this up. And we just started to do so. I managed to acquire funds to build like a 3 or 4 times larger version of this machine. This will then be 4.60 meters by 2.50 meters or something like this, and will allow us to do panels of maybe 1.20 meters by 1 meter, or roughly. And I would consider this to be the medium scale version of this process. And the final goal would be to scale this up again by a factor of 2 or 3 to actually reach, like, I don't know, 3 or 4 meter large panels. In all the math and physics used, there's nothing that really prevents this from scaling to these dimensions. But we will see what happens in reality.
So thank you very much. One last question from the audience before we move on to the next speaker.
I wanted to just connect to the answer that you just gave me. When you go larger, there will be aspects of self-weight, because
yes.
that will deform the membrane.
Yes.
How will you counteract that?
Yeah, it's a good point. And of course, this is already an issue here. If you scale everything down, the self-weight doesn't disappear. And the way we dealt with this here is by making sure that it is small compared to the other loads in the membrane. Right, so the main load in the membrane is this normal force created by the air pressure, or by the lowered air pressure. And by making sure that this normal load is, for example, 20 or 50 times larger than the vertical load you would get from the weight, they almost point in the same direction, not exactly, but almost. And if these are, like, I don't know, 50 times scale difference, then you can just ignore it. It doesn't change. And the same actually still works at larger scales. Even in this like 10 times larger 3 or 4 meter scale, of course you also scale the thickness of the membrane, and as a result you also have to reduce the air pressure further, and you can keep these two quantities apart by a factor of 20 or 25 or 50. So my guess is that it can probably be ignored even at larger scales. If not, it can be included as another term, of course, in this optimization. But I haven't tried this yet. And there is actually then a real limit in a way. At some scale, you would have to lower the air pressure below negative, like below zero, which of course doesn't work. So there is some limitation, but like a ballpark estimation is that even for a 4 meter panel, you can still add like 10 centimeters of concrete and still have a factor of 20 difference between the two.
Okay, thank you very much, Florian.
Yeah, so thank you.